For less than a century, humans have learned to use chemically propelled rockets to leave Earth and explore the solar system. Some probes have even managed to break free from the sun's gravity and are headed towards interstellar space. In the future, these probes will travel further and further into the galaxy, never to return to their original system. But is what we've done in recent decades something always possible, or have we Earthlings been somehow lucky? Could there be planets from which it is difficult, if not impossible, to escape? Let's try to understand. This time, we ask you to put yourself in the shoes of an inhabitant of a planet different from Earth. Imagine being on another planet in our galaxy, orbiting another star, and imagine that your civilization has reached a level of technological development that allows it to build chemically fueled rockets, like those we used to leave Earth and reach the other planets in the solar system. Imagine being ready for the great leap into space, but your planet is not Earth. It has completely different physical characteristics, has a mass several times larger than Earth's, and is what astronomers call a super-Earth. Super-Earths do indeed exist. They have been discovered in the last 20 years by astronomers hunting for exoplanets, that is, planets orbiting other stars. In the future, we will delve into the topic of exoplanets in detail, but for now, it is enough to know that these worlds, these super-Earths, are rocky planets but larger than our own. Not large enough, however, to be giant planets like Jupiter or Saturn. They are, in short, planets for which we have no examples in our solar system but that exist elsewhere in our galaxy. Some astronomers have even hypothesized that super-Earths could be habitable, perhaps even more so than our Earth. For now, let's limit ourselves to imagining being inhabitants of one of these super-Earths. Could we build a rocket to leave or to send our automated probes for exploration? The escape velocity from the surface of a planet depends on the planet's mass and radius. We've seen that the escape velocity from Earth is about 11 kilometers per second. A rocket that wants to leave our planet must exceed that speed. We've also seen that objects like neutron stars can be so compact and massive that the escape velocity becomes close to the speed of light. But a super-Earth is not such an extreme object. On the surface, it is simply a rocky world slightly larger than Earth. Typically, the radius of a super-Earth is at most a couple of times larger than Earth's. If it were any larger, it wouldn't be a super-Earth but a Neptune-like planet with a much thicker atmosphere. However, since we know the density of a rocky planet, it's easy to calculate the typical mass of a super-Earth. It's about 10 times larger than Earth's. We know of at least one exoplanet that has exactly these characteristics. It's called Kepler-20b and has a radius about 1.6 times larger than Earth's and a mass 10 times larger. So we can easily calculate the escape velocity from such a super-Earth. It comes out to be about 27 kilometers per second, an escape velocity about 3 times greater than what is needed to leave Earth. This isn't an enormous value and might not seem like a big problem to reach it. But here another aspect of the problem comes into play. The equation discovered by Konstantin Tsiolkovsky, also known as the rocket equation, which tells us how much chemical fuel mass is needed to reach a certain velocity. And here the problems begin because the rocket equation is an exponential equation. It means that if you double the speed you want to reach, it's not enough to simply double the fuel mass, but you must take the exponential of 2, which is about 7. And if you need to triple the speed, as you would need to leave a super-Earth 10 times more massive than Earth, you need about 20 times the amount of propellant you would need on Earth. In reality, things are even worse because the equation includes the exhaust velocity of the propellant, which depends on the type of chemical fuel used. But the thrust you get with that exhaust velocity, called specific impulse, also depends on the planet's gravity. And, all in all, it turns out that to leave a super-Earth like Kepler-20b, even using the best imaginable chemical propellant, you would need over 100 times more fuel than you would need to leave Earth. And that's for every kilogram of mass to be taken into space, not accounting for the rocket's weight itself. Just to give an example, the Saturn V, which brought the first humans to the Moon, had a mass of 3,000 tons at launch and carried a payload, meaning excluding the propellant, of 45 tons. For the same payload, a similar rocket on a super-Earth would need about 400,000 tons of propellant, equivalent to the mass of an Egyptian pyramid. It's not a physical impossibility, of course, but it would make the endeavor truly desperate. If the planet were just a bit larger, with a mass exceeding 10 Earth masses, the task would become practically impossible. These results were published in a 2018 study, which you can find in the description. These are fairly simple calculations, based on basic physical principles, so they are not avoidable. Of course, one could think of other methods that a civilization on a super-Earth might use to reach space, but some of these would still be complicated. For example, in an upcoming video, we'll talk about the possibility of building a space elevator. It would be a difficult endeavor on Earth, but it would be incredibly more so on a super-Earth. All the problems we would have on our planet, such as finding a material sufficiently light and strong enough to build the elevator, would be even more serious on a planet with greater gravity. That's why, if there really were a technological civilization on a super-Earth, probably the only way it could reach space, according to our current knowledge, would be to use nuclear propulsion. But super-Earths are not the only type of planet from which reaching space would be difficult. Take, for example, a planet orbiting a star with a mass smaller than the Sun, like a red dwarf. Red dwarfs are the most abundant stars in the galaxy, and many of the rocky planets discovered in recent years orbit this type of star. For instance, the closest star to the Sun, Proxima Centauri, is just such a star, and we know, among other things, that it has a planet orbiting in its habitable zone, that is, at the right distance to possibly have liquid water. Now, let's imagine that any inhabitants of this planet around Proxima Centauri wanted to send a probe out of their star system, as we did with the Voyager probes. From Earth's orbit, the speed needed to leave the solar system is about 40 kilometers per second. To reach this speed, the Voyager probes used the gravitational slingshot effect with Jupiter. Now, one might think that escaping the gravity of a smaller star than the Sun would be easier, but in reality, a planet in the habitable zone of a red dwarf must be closer to its star than Earth is to the Sun. So, even though a red dwarf is less massive, the gravity in the habitable zone is stronger. For example, Proxima has a mass of about 12% of the Sun's, but the habitable zone is 20 times closer to the star than it is around the Sun. The reason is simple. A red dwarf is less luminous and less hot than a star like the Sun, so if you want the planet to have a temperature compatible with the presence of liquid water, you need to be closer. The moral of the story: the escape velocity from there is higher than from Earth's orbit. This has been analyzed in another study, also linked in the description, and this study also concluded that launching an interstellar probe from a planet around a red dwarf would be very difficult using chemically propelled rockets. Of course, this doesn't mean it's impossible. For example, you could use a laser-propelled sail. All this, as I said at the beginning, is mostly an exercise of imagination, but it helps us better understand how the physics behind space exploration works. And it also helps us realize how many things we take for granted depend on a series of factors that don't always repeat themselves in the same way elsewhere in the universe. In this sense, it wasn't at all guaranteed that our species would manage to reach other planets and, perhaps, in a distant future, other stars. Despite the difficulties, we had the opportunity to explore space beyond our planet. Think about how many things we would have had to give up if reaching space had been immensely more difficult and expensive. Not only would we not have telescopes and space probes, and thus would have understood much less about the universe, but we wouldn't even have practical things like artificial satellites, and thus intercontinental communications, satellite maps, and so on. In short, we've been lucky. We don't live in a space prison. Other intelligent species on other worlds, if they exist, might face much greater challenges than we do. Thanks for watching. Please like the video and subscribe to the channel.